Hey guys, this little clip goes with roughly goes with section 11.2 of your text. If you'd like to read that, peruse that sometime. This little diagram is similar to one in your textbook, but it's actually a little backwards. But gives me the reminder that it really doesn't matter what you call H1 and H2. Anyway, I have some solvent, and the solvent might be water, or it might be something nonpolar. But I'm thinking about mixing the solvent with some solute crystals in a nice geometrically regular arrangement. And what I want to do in order to make the mixture, I think about actually separating these solvent particles a little bit so that they're further apart and ready to mix with these solute particles. But I also have to think about separating those particles, overcoming the solute particle interactions here with something called delta H2, or up here it would be the solvent particle interactions. I would be separating them a little bit, called delta H1. Both delta H1 and delta H2 are both positive. I have to add a little bit of energy into overcoming these solvent particle interactions to make them further apart. Same story down here. I have to add a little bit of energy here. This could even be associated with the lattice energy, something we talked about a long time ago in this solid crystal, taking these ions apart, or the particles apart if they're like a molecular solid crystalline structure. In any case, then over here, when the solvent particles are separated and ready to go, and the solute particles are separated and ready to go, I just allow them to, I imagine them falling together to make a mixture, a nice uniform, random, chaotic mixture. Called the solution, and there's an amount of energy that goes along with that as well, called delta H3. And like I said, I think this one and this one are switched in our textbook, but it really doesn't matter as long as you keep them straight in your head. One amount of heat or enthalpy is required to separate the solvent particles from each other, and the other required to separate the solute particles from each other. Or in other words, if I take the energy to separate the solvent particles, which is probably endothermic, and the energy to separate the solvent particles, oops, darn, that should be solute. Okay, let's see, how is it listed up here? Here I have the solvent particles as H1, the solute particles as H2, so I need to change this to solute, and I will do that before I put the PDF online, darn it. So, alright. So this is the solvent particle separation, the solute particle separation, solute particle separation, and then when these two separated mixtures, I imagine them falling together to give the delta to also have an energy change associated with that, but all those together result in what I call the delta H of solution. By the way, this is usually exothermic, and these are usually endothermic, so this will give off some heat, this will take in some heat. Again, that's a typo with my hand. I got to change that. That's solute, according to what I had written up here. H2 is a solute separation. All right, darn. Best laid plans. And what I said a second ago, delta H1 and delta H2 for separating the solvent and the solute, almost always positive, endothermic. I have to put energy into the system. But then when they fall together or come together with each other, that delta H3 is usually a negative, exothermic. So if it's largely exothermic, then I probably will have some kind of solution formation. I'll probably have a mixture. But if it's just slightly exothermic, I don't know if this is large enough to overcome this, or when I say overcome, I mean compared to the sum of those two. Will it be sufficient to allow a solution to form? Here's a diagram trying to describe what I was saying up there. By that I mean, here are my solvent particles. Separate them, delta H1. Solute particles, separate them, delta H2. And that requires, both this and this require the addition of some energy. But then when I have my solvent and solute particles separated sufficiently, they can, quote, fall down the energy hill. Although that's a little bit loosely speaking, but I think about it that way. They fall down the energy hill, releasing some energy, and if I compare this overall delta H3 to the delta H1, delta H2, if that's larger, the red one here is larger than those, then I'll have an overall exothermic process, and this solution may actually heat up a little bit, so some energy is given off overall. On the other hand, conversely, here I have a delta H1 and a delta H2 that's pretty large. That looks like that solute lattice energy is pretty high, so I'd have to add a whole bunch of energy into that. And then I say, how would this energy released when these two fall together compare to the sum of those two? In this case, it's endothermic, and I'm not so confident this would end up happening. It might. Depends on one other factor about how chaotic this system is. If it has a high degree of randomness, there's a good chance that it might decide to go ahead and form. Nature strongly favors processes that are exothermic. So this one would be very favored. This one would be less favored, but there are some good examples of this. Maybe I'll give a demonstration in class with regards to that. Another common term sometimes thrown in is called the enthalpy of hydration, or I'm imagining the water particles, well, it could be water as a solvent or the solvent particles in general, separated, and then they fall down and surround the solute particles. So in our above diagram, anyway, I think this might be, sorry, I apologize about that. Oh yes, as I was saying, another common term called the heat of hydration, the enthalpy of hydration, when water surrounds the solute particles, separated solute particles. Notice I'm missing the delta H2 here, the energy required to separate the solute particles. They're already separated. But this is the energy associated with the separated solvent combined with the surrounding of that solute particles. Here's another key phrase. I'm pretty sure you've heard it. Like dissolves like. That means water, which is polar, dissolves other polar and ionic substances really well, but not oils and waxes. But something like an oil or a wax would dissolve any other compound that wouldn't dissolve in water. And that's usually a good rule of thumb. It almost always works. Now, just in case you don't remember what polar means or what a polar molecule looks like, let me show you a few. Well, here's water. It has H2O, and it's lopsided and bent because of a couple of lone pairs sticking up off the oxygen up here. Very bent, very lopsided geometrically, and the bonding is not electronegatively the same. So this is a polar molecule. It's very lopsided. Another lopsided one is NF3 or NH3. This one would mix really well with this one, and this one would also mix well with this one. This is an alcohol, C2H5OH. This is acetone, a nail polish remover. This also is fairly polar, as CH3, C double bondo, and CH3 over here. That's lopsided, used as a solvent in other situations. And here I see a model of how water, being polar, lopsided, can surround the sodium ion or the chloride ion or many other ions in a salt and pull the crystal structure apart. In a simple model, we say the positive side of the polar molecule attracts the negative ions, or the negative side of the polar molecule attracts the positive ions, the cations. And they're called maybe ion dipole forces. The dipole is water, and the ion is, probably the positive negative that comprises the salt in question. Or here's some nonpolar molecules. Water's polar. This looks like, ethane. 2 carbons, 6 hydrogens. Carbon dioxide is nonpolar as well. So carbon dioxide could be used as a solvent, either under a lot of pressure or something like that. I know carbon dioxide is used as a solvent to dissolve caffeine out of coffee, or also used in some dry cleaning situations. This is called carbon tetrachloride. Carbon tetrachloride, very not lopsided, very symmetrical, and so it's a nonpolar solvent. And hexane, 1, 2, 3, 4, 5, 6 carbons, and the surrounding hydrogens is a very nonpolar solvent. So hexane wouldn't dissolve in water, but hexane would dissolve other things like waxes and oils that water can't dissolve. All right, questions. Which would dissolve better in water, and which would dissolve better in octane? Nonpolar, polar. Here's a salt, potassium iodide. Water or octane would dissolve it better? I think it's water. This one's methanol. It has a carbon here and an OH group over here, CH3OH. And I'm going to have to say hexane or water would dissolve methanol better? Water. All right, let's see. This is a larger hydrocarbon, C12H26. Looks pretty regular and symmetrical, and I see no oxygens, no hydrogens, no lopsidedness to it. I'm going to have to go with hexane on that one. Here's a DDT, an abbreviation for long ago used insecticide. Rings of carbon, hydrogen, some chlorine. That doesn't look very much like water. I think hexane might do a better job of dissolving that. Here's a couple of interesting common molecules. Sucrose, table sugar, has a whole bunch of carbons, some oxygens thrown in here, but more importantly, OH. Almost every carbon has an OH group on it. Because of those OH groups, and those OH groups look just very similar to water, HOH or H2O. Sucrose, as you know, dissolves very well in water because of those OHs. If it weren't for those OHs, if I took the OH group off, took it off, remove those in some kind of chemical reaction, I'd have some hydrocarbon with some oxygen thrown in that probably wouldn't dissolve in water very well because it's so large, and it would be hard for the water molecules to surround that sufficiently with sufficient strength and force to attract it away from its buddies. Vitamin C, what do you think? OH. Is vitamin C water soluble? I think it is. This over here might help a little bit too, but it's definitely got some polar parts to it, and the geometry would most likely allow vitamin C to dissolve in water. What about vitamin A? Vitamin A has a whole bunch of hydrocarbons and only one OH group way over here. Can you tell by the framing of my question? I don't think this will dissolve in water very well. It's probably fat soluble. So in a sense, it would not be eliminated by the body easily. It would be more easily retained by the fats and the oils in your tissues. Here's a space-filling model of that vitamin A. Kind of interesting with the one OH group over here. OH group right there. Ammonia, polar or non-polar? NH3, yeah, very polar. Dissolves in water. Sulfur hexafluoride. I don't think it's going to dissolve in water too well. It doesn't look very polar. I'd go hexane on this one. Here's a saturated fat, and here's an unsaturated fat. Saturated means it has as many hydrogens surrounding the carbons as possible, no double or triple bonding. This looks like it wouldn't dissolve in water too well. It's got a little polar side over here, but that's relatively unimportant compared to all these carbons. But on the other hand, if I took off a whole bunch of carbons, what if I just had CH3COOH? That would dissolve in water. That's called vinegar. But the more carbons I add to that little chain, the less soluble it becomes in water. And this doesn't make much difference in terms of water solubility. It's such a large carbon chain with no OH groups, not many OH groups around. It's not going to work. Yeah, that looks like it. Thanks for watching, guys.